Okay, let's continue on with our chemical shifts. Now we saw the first characteristic was the number of protons, the number of signals, right, in a NMR spectra. The next characteristic we're going to talk about is chemical shift. In many NMR solvents, 1% of TMS, tetramethylsilyl, is added as an internal standard. Now, it's because of the frequency of those protons in the 4 methyl groups on TMS that we actually use this kind of as our ground zero, our point of zero. The shift for all of our proton signals are calculated as a comparison to this TMS, right? So we'll put TMS in our sample just so that we know where our 0 point is, and then we do this fancy calculation for the chemical shift itself. You do not need to know the calculation, but it is going to be based off of the TMS shift and the frequency of the instrument in hertz. Now remember that instrument is a big old magnet, and so it's really based off of the type of instrument you have that is dependent on how accurate your shifts are or how clear your shifts are. So for instance, if you have a 60 megahertz instrument, the hertz would of the chemical shift, the delta there may be different, which is dependent on if you had a 600 megahertz instrument, right? So why we use TMS is that internal standard so that no matter what size of magnet you have in your NMR, you actually will have a constant chemical shift. So we can use a chart to actually identify certain different types of protons, just like we saw in the IR. Now, the shift relative to TMS is called a chemical shift, or it's that delta. It's a dimensionless number, meaning it's unitless, right? Because the hertz cancel each other out in this calculation. Units for delta are often given in ppm, parts per million, which is just the indication of the magnitude there, right? Because the operating frequency is usually much greater than an observed shift in the TMS in terms of the frequency factors. So most proton NMR signals appear between 0 and 10 ppm. Sometimes that can even go up to 12 ppm. But again, we'll see that when we start looking at the different styles of protons that we have. Now, NMRs range are constant. Those chemical shifts are constant. There will be a table that is on our worksheet when we get to class that will, again, look at all of those chemical shifts based off of predicted environments, different protons attached to carbons, nitrogens, oxygens, etc. What we want to be able to decipher, again, just like in IR, is the idea of what makes things shift to a greater ppm, what makes the protons appear at a lower ppm. So why do they appear in this range along the x-axis, right? And so this is a typical NMR, and this is just going to be one so that we can start dissecting and knowing what certain definitions are. Low field strength is what we call downfield. These downfield protons are the protons that appear on the spectrum far to the left of our screen. Now, why they are downfield is because they are protons that are de-shielded, meaning there's probably some sort of polar environment pulling electrons away from the nuclei. Remember, chemical shifts are going to be determined based off of the amount of energy caused to resonate, the alpha and beta spin states. And so when we're looking at a de-shielded proton, they appear to the left of our screen, on the left of our spectrum. High field strength are what we call upfield. These are more shielded protons. These would be things that are have a greater magnetic force acting on them because they are looking at having more electrons around the nuclei, and so the magnetic field can't get in there to affect them as easily. Shielded protons require a stronger magnetic field to excite at the same energy as de-shielded protons do. Currently, NMRs analyze samples at a constant field strength over the range of energies, and so that's why we see this chemical shift occur. Shielded protons also have smaller magnetic forces acting on them. So because of the electrons kind of shielding them around the nuclei, right? So they have a smaller energy gap. And so they absorb technically a lower energy of radio waves. And that's why we also see this chemical shift is lower value of ppm. So where I write high energy here, these de-shielded protons are actually have a larger energy gap, and they're absorbing more energy from the radio waves, not magnetic field there, the high energy radio waves. And then the low energy here on the upfield, because electrons are still surrounding the nuclei, they are shielded protons, shielded nuclei, then they tend to absorb lower energy radio waves. Alkane protons generally give the signals around 1 to 2 ppm. Things that are non-polar are shielded. Why? Because the electrons are still around the nuclei. As we start to incorporate more polar atoms, what's happening here, right? Remember, we have our dipole moment. The electron density is being pulled more towards the halogen. The more polar that halogen becomes, notice what happens to the shift. More electronegative, more de-shielding of those protons. The red protons are going to appear further downfield because they are more de-shielded. The electrons around them are being pulled towards the fluorine to create the dipole delta minus there that I drew for all of the halogens. And so that is why we see changes in the shift. Now, for a typical molecule, we see here we have one chloropropane. The hydrogens that are closest to the chlorine, closest to the electronegative atom, are the most de-shielded, so they appear furthest downfield, furthest to the left on the spectrum. Then we have the middle, the next closest, and then finally that CH3 group. Notice how we're counting this. We're not using numbers, we're using alpha, beta, gamma, ABC, just in our Latin and Greek letters here. And so be very aware of the idea that the closer a proton is to an electronegative atom source, the more de-shielded, so the more downfield those protons will be. Again, if we increase more electronegative atoms, what do we get? More de-shielded. Now, with predicting chemical shifts, what we want to be able to say is that certain protons start at a specific position. Now, technically, what we're going to be looking at is that a CH3 group typically starts at around 0.9 ppm. A CH2 group, this is what we call a methylene group, where we have a carbon with 2 hydrogens and then other bonds to somewhere else, usually starts at about 1.2 ppm. And then a methine group, a C with 1 hydrogen, usually starts about 1.7 ppm. These values you should know. I will be expecting you to do some calculations with these, with the effect of these protons based off of other things around them. Looking at this table, 15.1, what's really important to understand is that other atoms such as oxygens, chlorines, fluorines, things like that, are going to be shifting these even further. So these are what I want to call our base shift, right? Our baseline chemical shift. And then what happens is neighboring functional groups will have an effect on this chemical shift, will have an effect on this baseline. And so if that is an oxygen from an alcohol or an ether, what we see is the effect on those protons is plus 2.5 ppms. So you have a methylene group. Notice the CH2 group right here. That is a methylene group. Its base is 1.2, like we just talked about. Because it's next door to an oxygen, we can predict its shift would be 2.5 more, 3.7. The actual chemical shift for those CH2 groups in ethanol is 3.7. Excellent. Now, an oxygen of an ester is quite different because it has that extra carbonyl group. Notice that this oxygen right here is directly connected to the two protons in question. That's the functional group setup that we're talking about. When that occurs, the baseline chemical shifts get added 3 ppm. So methylene group, again, we start at the 1.2, we add 3, we predict a 4.2, actuality 4.1. That's not bad, that's pretty close. Carbonyl group, if you just have a simple carbonyl group, that could be the carbonyl group adjacent to your protons of an ester, an amide, a carboxylic acid, whatever. You're closer to the carbonyl group. Those CH2 groups will be adding 1, right? So this chart is really helpful to identify what types of shifts to expect. All right, let's take an example real fast before we move on. I'm going to do this carboxylic acid. And the first thing that I want to make sure is that we draw in all of the protons. I'll draw this methylene group with wedge and dash, not chiral, but again, important to identify whether they're chemically equivalent or not. And then there's 3 hydrogens on the end there with that methyl group. Now, we would expect 3 chemical signals from this molecule. 1 would be the carboxylic acid, 2 would be the methylene group, 3 would be the methyl group. Now let's predict the chemical shifts for the group 2 and 3. We would not need to predict the chemical shift for our carboxylic acid. We'll see that he is predictable on a chart right around 12 ppm, somewhere between 10 and 12 ppm. All right, let's talk about the methylene group first. Typically, methylene groups are 1.2 ppm for their chemical shift baseline. We see that that methylene group is adjacent to a carbonyl. Yes, it's adjacent to a carboxylic acid, but notice that the oxygen of that carboxylic acid is not directly connected to the methylene group. The carbonyl is directly connected to that methylene group. So we will add 1 for the carbonyl group effect on our alpha protons. Alpha being the first carbon adjacent to that functional group. So we would predict 2.2 ppm for this proton set. All right, now if we go and look at beta, the next door to the carbonyl, right? Alpha comes first, then beta. Betas have about 1/5 of the effect that the alpha protons do. So methyl groups, we would predict, just like we saw before, baseline of 0.9 ppm plus 1/5 of what the alpha does, 1. So 1/5 of 1 is 0.2. So we would predict that those 3 protons show up around 1.1 ppm. We will practice this more together in class, but this would be one example of mathematical calculations that I would need you to understand and be able to perform. All right, anisotropic effects. All right, so these are looking at when an electron is in a pi system. So benzene is the best example here. And so diamagnetic anisotropy, right? Very difficult to say, sorry. This idea here is looking at an induced magnetic field with the actual NMR, and the protons being de-shielded by that induced magnetic field of the circulating pi electrons. And this is what we call a ring current. So what's important about this? It means that there are different regions of localized space and they have different magnetic strength. And so regions outside the ring, on the outer edges of the ring where these protons are, have an increased magnetic field. more of the ring current is existing in the middle of our ring versus the outside of the ring. What this does is it actually creates the aromatic protons. We'll talk about aromatic rings. Benzene is our biggest example for aromatic compounds at this point in our chemistry careers. They appear extremely downfield because of this effect. They are very de-shielded aromatic protons. They appear on the outside of the ring, where most of what this effect is doing is most of the induced magnetic field is occurring inside. The electrons are moving inward towards the center of the ring. And so the outer protons actually require more energy to spin flip those protons. Aromatic protons appear usually around 7 ppm. And so that's where we want to be able to observe those aromatic hydrogens, typically on benzene for us. So here is the idea of the chemical shifts. This chart will be on our worksheet as well as we start to navigate and understand some of these. I do expect you to recognize the methyl, the methylene, and the methine group, the CH3, the CH2, and the CH baseline peaks. I do expect you also to understand table 15.1, the effects of oxygens, whether that's an oxygen of an alcohol or ether, the oxygen of an ester, or the carbonyl. And so those are our calculations that we just practiced. Everything else would be more of a locate and represent on our chemical shifts and not so much any calculations after that. Integration. When we're talking about integration, we're really representing the area under these curves, because the area under each of these curves is going to be able to be quantified to the relative number of protons. This is something we were not able to do with IR. We now can take the area under these curves and start to identify how many protons are represented. Now a computer will calculate the area under each peak. Thank you, computer. Back in the day, this would have had to have been done by hand with all of the math that we ever have learned in calculus. Very happy that we don't have to do that. Now, how a computer technically does it is what we call a step curve. And so they give integration values typically at the bottom of the spectrum. Now, if you have a really cool computer, you can set that computer to make the peaks into whole numbers. How do we do that? We usually divide by the smallest. So you take all of them and divide by 27 here. And you try to make them whole number ratios. This kind of should remind us of how we found molecular formulas back in the day in general chemistry from mass percents or amounts in grams, trying to find that whole number ratio, right? Divide by the smallest. Now we cannot have 1.48 protons, right? Or 1.5 protons being represented in a signal. So then what the computer then does after it sets the values for the other peaks by dividing by the smallest, it will take and make those into more whole numbers, 2, 3, 2, and 3, by multiplying by some factor to make them whole numbers. Here, the factor would be multiplying everything by 2, right? All right, so this peak represents 2 hydrogens. This peak right here represents 3 hydrogens. This group of peaks is 2 hydrogens, and this one is 3 hydrogens. That's literally what integration does for us. It tells us the relative number of quantities for the protons rather than the absolute, all right? So it's giving us the smallest whole number ratio of those peaks. So symmetry can affect these integrations. This is 3-pentanone, 1, 2, 3, 4, 5. It's a pentane with a ketone in there on carbon number 3, so that's why it has the ONE ending. 3-pentanone has 2 kinds of protons. Let's just redraw this guy and draw them out. I'll use some fancy colors. These 2 protons are the same as these 2 protons, and these 3 are the same as these 3. So we could expect to see 2 signals, 6 hydrogens versus 4 hydrogens. But what the computer doesn't really understand is that this is a molecule, right? The computer just understands numbers and smallest whole number ratios. So it would spit out a value of 2 to 3, not 4 to 6. All right, so be aware of symmetry. And so what we would see is this type of an idea where we're at 35 or 32.5, we'd say divided by 32.5 divided by 32.5. We'd find the smallest whole number ratio, and it would be a 2 to 3 ratio. What you would note is that if you were given a molecular formula, which typically you are, you would say, well, hey, 2 plus 3 is 5. That does not add up to 10. So I can actually take those integration values and make them double, right? 4 plus 6, same 2 to 3 ratio, just adding them up to my CH10 there. All right, excellent.